Right, so now, just going straight on, we're in the middle of trying to specify the formal description of big N for the operator, the regular operator of concatenation. So we got to the point of trying to find the transition function. Well, similar to the case before, and again, I have the same problem here that I, as yet, don't understand. As a prof, I think I understand most things. I'm able to explain them to you, but since I don't, since I cover so many topics, pure math and math physics and computer theory. That's a huge range of materials. So, and I'll be covering many topics over the years and decades, hopefully. So, I cannot be a real expert, like with decades of experience in a particular topic. That's just not realistic. So, anyone trying to do what I'm doing, probably, unless they're absolutely brilliant, there will be moments when some things, a very small minority, hopefully, of some things, that prof, in my case me, just doesn't get. We're all human, right? Everyone has limits. So, I admit I'm puzzled by this. And I say I don't know whether it's the fault lies in me that I've missed something, or maybe with Sipser, or a bit of both. Anyway, okay. So the transition function for this big machine N, which is supposed to recognize concatenated strings x, y, where x is a string belonging to language A1. And y is a string belonging to language A2, right? So here of this form. Now this and this, these three make sense to me. This one hold on. No, this and this, those three make sense to me. This one puzzles me because how can you have a label that's not eta when on the diagram you can't see it in the previous session. The label on the arrow was eta. So anyway, okay. So if you're in the process of detecting or accepting the string x belonging to A1, you'd be in here, right? So your current state is belonging to the set of states in Q1. That's in machine N1, and your machine N1 is detecting hopefully your x, the string from language A1. Okay, so you would use the transition function from machine N1. And similar logic, if your current state, you're in machine N2 and you're in the process of hopefully accepting string y, you would use the transition function d2 for the machine N2. Okay? So those two sort of make sense. Now, special case here, your current state is you're in F1. That's one of the accept states of machine N1, of the automaton N1. Okay. Now you follow the arrow, the eta arrow, and you pick up the state that the eta arrow is pointing to. In other words, the starting state of machine N2. Well, that's Q2, right? So whatever that is, you'll union it with Q2, due to the eta arrow. So the set of next states will be this, and you'll have a machine, for each whatever that is, how many states there are in that set. you'll have a machine corresponding for each one, and that machine will then independently move down in time. it will process independently. Okay, so that makes sense because of this. This one, that's the same problem I had before, and I don't get it. When I don't get something like that, it sort of nags on me. It stays at the back of my mind, and then something will pop up, and then hopefully flash. But I haven't got there yet. So I'm hoping it'll come to me when I solve a lot of the problems in the end of the chapter. All right. So this one I don't get, because your current state is at one of the accept states for machine N1, and it then seems to me that there should be beta arrows on, they would then be the labels of the transitions, the arrows to the starting state of N2. So I don't see how can this be not equal to beta? I don't understand. Seems to me nonsensical. But you've done it twice, so I'm missing something, and I don't yet understand what it is. Now, if if you can see what it is, please email me. Now, since these videos, these clips last forever, using common sense, like if it's like 10 years from the year whatever, 2012, when I made this video, it's likely I figured it out. Okay, so don't rush off and email me many years after this video was made. So common sense, right? Okay. All right. So we made the. Once you finish that, you've constructed your machine N, your DFA, that detects the concatenation. So in other words, the language of concatenated strings, the language A1, little circle, A2, that language, the concatenation of two languages, it has a machine, big N, that recognizes it. Okay? Therefore, that language, A1, little circle, A2, is a regular language, okay? Because it has a machine, an NFA, that recognizes it. And therefore, that concatenated language, A1, little circle, A2, is a regular language. And therefore, that the set of the set of regular languages is therefore closed under the operation concatenation. Okay, now the third one of the three. So a similar theorem statement with just one word changed. So now we have star operation here. So the class of regular language is closed under the star operation. Okay, now can you remember what star means? It's a little different. Instead of having two languages, we only have one language. So star is a unary operator, the star operator. And what it does is it creates. I've not heard anything to the contrary, so I'm assuming that the set A star, or A1 star, is in fact an infinite set, countably infinite, but infinite. And if you star a set, what are you doing? You're creating all possible concatenations of strings of that language. For example, say you concatenate 0 times. Well, that would be the empty string. If you then concatenate just sort of once, well, in the sense, so your concatenation would be just the individual strings of that language. You know, string 1, string 2, string 3, and you put them all into A star. Okay, and then you have the concatenation with two strings, all possible concatenations that have two of those two strings of that language in it. So you might have string 1, string 1, you might have string 1, string 2, you might have string 1, string 3, string 1, string